This is the lecturette for section 12.5, which involves examining phase diagrams. So in this example, we're going to look at phase changes involving solids, and then we'll look at phase diagrams as predictors of what phase a substance will be in based on its temperature and pressure conditions. We'll examine what supercritical fluids are, but rather briefly. And finally, we'll look at phase diagrams as predictors of phase changes. And so let's start by looking at phase changes involving solids. We looked at those for liquids before, where we looked at vaporization for liquids. When we think about solids, what they do is they melt, and the enthalpy involved with melting a solid is called the heat of fusion. And so we look at the heat of fusion for a bunch of different substances, that is melting them, and their melting points. What we always see is that the heat of fusion is always significantly smaller than heat of vaporization. And that's because changing a solid to a liquid, that is melting it, takes much less energy because you're not actually separating the molecules all the way from each other, you're just allowing them to move past each other, but they still have significant intermolecular forces. To go from the liquid phase to the vapor phase, you're completely breaking all intermolecular forces, which takes a lot more energy. So vaporization takes a lot more energy than fusion, and therefore boiling points are much higher than melting points. The phase changes can actually be added together. That is, you can look at fusion, solid going to liquid, and liquid going to vapor. Those together are the same thing as taking a solid directly to a vapor, which is the heat of sublimation. One of the things to note is that if you can actually measure the heat of sublimation for a solid, it isn't always equal to the heat of fusion and heat of vaporization added up exactly. And the reason is that these values, the heat of fusion and heat of vaporization, are often measured at different temperatures. And because of that, there are slight differences when the temperatures change. The enthalpy, at different temperatures, the enthalpy to melt something or the enthalpy to vaporize it is actually slightly different. Not very different, but a little different. And so you generally get, if you use this method, you get a good estimate of the sublimation, but it will often not be exactly what the energy of the sublimation is. This is the phase diagram for water, and so let's first look about how it's constructed. The idea is temperature increases on the x-axis from low, meaning cold, to high, meaning hot, and pressure increases on the y-axis from low pressure to high pressure. Notice that at low temperatures we have what's called the solid state. So that's the solid of the solid state for water. At high temperatures we have the gaseous state. So molecules are separate from one another here. They're rigidly held in a cage here. And in the middle is the liquid phase. And all phase diagrams involving simple solids, liquids, and gases always have the liquid sandwiched between the solids and the gases. Notice that there's a temperature below which, this temperature here, below which the liquid can't exist. That temperature, this temperature here, is where the liquid, the solid, and the gas can coexist all together in what's called equilibrium. That's a pictorial version of that there. And that's called the triple point. So at temperatures below the triple point, you can't have liquid anymore. And so solid will go to gas, that's called sublimation, and gas will go directly to solid, that's called deposition, in addition to the other phase changes you've had before. Okay, so let's move on from this. You can look at phase diagrams as predictors of phase. The first thing you can notice is that if you look at 1 atmosphere, the temperature at which the 1 atmosphere crosses the boundary line between the solid and the liquid, that's the melting point. That's the normal melting point. Meaning normal, meaning the melting point measured under 1 atmosphere. And or freezing point. Same thing in either direction. And the place where 1 atmosphere crosses the liquid gas line as the normal boiling point. This line right here, by the way, is the same thing as our vapor pressure curve we saw earlier. The vapor pressure curve we saw for a liquid rising in temperature is the same thing as the boundary line in a phase diagram between the liquid and the gas. Here again, of course, it's a triple point. The other thing to notice is that there's a point up here called the critical point. And at temperatures above the critical point, you no longer have a normal substance or normal substance in the sense that you can't compress the liquid and make it into a gas. And that's a supercritical fluid above those temperatures. But what you can do is, with a phase diagram, is you can just look at any particular point and decide whether the species is a solid, liquid, or gas. So let's say we have water at 50 degrees Celsius, and 200 atmospheres pressure. What you do is you go to 50 degrees about here, and about 200 atmospheres about here, and you go to there, and it must be a liquid. If you had 50 degrees and say you had like a minus 20 degrees Celsius and 200 atmospheres, you'd be minus 20, you'd be around over here somewhere, you'd be around here somewhere, and you'd be a solid. So you can determine what phase you'll be in just by mapping where you are on the phase diagram. The critical point is the point above which the gas has too much kinetic energy that you can ever form a liquid with it. The molecules have too much energy. They're always staying apart in a phase that's like a gas. But if you put it under really, really high pressures, the molecules are actually very close together. So they're close together like a liquid, but they're actually not bonded together like a liquid. And that's a special form of nature, a special form of way of being, and that's called a supercritical fluid. Supercritical fluids have very different properties from either liquids or the gases of that same compound, and they're industrially very important. And so what will happen is above that pressure, what will happen is the gas will be called a permanent gas, meaning you can't compress it to make it a liquid. Below that pressure, you can talk about the gas being an impermanent gas, meaning you can pressurize it and turn it into a liquid. And here are just some critical temperatures for a bunch of different compounds, but some of these are commercially very important. So for example, most natural gas is made of methane, and the critical temperature for methane is minus 82 degrees Celsius. And that means if you want to liquefy methane and carry it around in a truck or a tanker out at sea, in order to get it very dense and hold it without having lots of pressure, you have to have it be very, very cold. You have to cool it down a lot to get it to be a liquid if you're ever going to do that. Otherwise, you have to carry around just high-pressure gas. Finally, the last part of this is talking about phase diagrams as predictors of phase changes. And the idea is what you do is if you say, okay, if I'm at this point here and I increase the pressure, so remember, you'll always have solid, liquid, gas. If you increase the pressure to here, what will happen is you'll go from gas to liquid. So that will liquefy. That will be condensation. If, on the other hand, you're here and you increase the temperature to here, that will be vaporization because you're going from the liquid to the gas. If, on the other hand, you're here and you go to there, that will be liquid to solid. That will be freezing. If you're here and you go to there, that will mean you're going from gas to solid, so that would be deposition. And if you were here and you went to there, that is, you lowered the pressure and you went from solid to gas, that would be sublimation. So you can just look on the chart and decide what's going to happen. An important aspect of this is one of the things that's special about water. This particular phase diagram is similar for almost all states, almost all matter, where if you're at a particular place near the solid liquid line, you increase the pressure, you'll turn into the solid. And that's because that happens because the solid is more dense. And because the solid's more dense, when you put pressure on it, the liquid will turn into a solid because the solid takes up less room. Let's go back to our phase diagram for water here. What happens here, if you're right here with water and you're solid and you increase the pressure on it, it will turn into a liquid. And the reason is that for water, the solid is less dense. And water and only a couple other substances in all of nature has this being true. So in water, what happens, what's special about water, is the solid liquid line actually tilts to the left. Whereas all other, so that's water, and basically all other substances, that line goes that way. And that's it for phase changes.